Now let's go through two examples on Amazon. The first one will illustrate the point that Bayesian ranking can change the order compared to a simple naive averaging. And this is data from someday in 2012 on Amazon with 5 different kinds of MacBooks. And in this table we list the number of ratings, the naive simple average of these ratings, and the resulting rank. And our goal is to compute the Bayesian ranking and the resulting Bayesian rank. Okay, so first of all, we see that the total number of reviews, n in this case, you add these up, is 227. And the n times r, which equals ni times ri, this is each of the 5 products number of ratings, and ri is each of 5 products average ratings. That turns out to be, you can just multiply and then add up the 5 numbers to be 2332. Okay, 0.752. Okay. So the average rating therefore is about 4.42. If you look at these 5 MacBooks without computing any Bayesian numbers yet, you see that this one's ranked number 1 by average, simple average, and this one's number 2, but they each got only 10 or 15 ratings. Now we can go into the distribution, into the time series analysis, and all that we mentioned at the beginning of the lecture. But the mature results we have really is just on Bayesian adjustment. But just on Bayesian adjustment, already see that maybe they shouldn't be ranked so high, even though this is a very high score, 4.9, but it's only based on 10 ratings, whereas this 4.5 stars is based on a much larger population. So maybe this should be ranked higher than this. Will that happen? I don't know. We have to carry out the calculation. We'll also see that these two average rating is actually below the overall average of these 5 products in the same category, whereas the other 3 are above it. Okay? The implication will come back in a couple of minutes. So let's compute, for example, R120. This is the Bayesian adjusted average rating for product 1. That would be 2332 n times r plus 10 times 4.92. Okay, 10 times 4.92. 10 is n1, 4.92 is r1. Divided by n, which is 527 total number of reviews, plus ni, the number of reviews for just this product, which is 10. Okay, so clearly, this 10 times 4.92 is one of the 5 components of this term, and 10 is one of the 5 components of this term. And the resulting number is 4.436, which is much lower than 4.92, because relative to the total number of ratings, 10 is a small number. So the Bayesian adjusted average is 4.436. We calculate the same formula for the other 4 products, we get these 4 numbers. You can look at the comparison before and after the Bayesian adjustment. This one got almost half of a point down, and this one also drifted downwards. This one drifted downwards a little bit, and this one actually drifted upwards, and so is this one a little bit. Now the Bayesian ranking turns out to be this MacBook is number 1, then this is number 2, then this is number 3. These two are basically tied. The difference is very small, basically tied at 4 or 5. If you look at this ranking compared to this ranking, you see that exactly different for every single product. 1 becomes 2, 2 becomes 3, 3 becomes 1, 4 becomes 5, 5 becomes 4. In this particular example, which is a little extreme, the Bayesian ranking actually completely changed the ranking order. Not single product out of 5 remains the same position. But it's intuitively making a lot of sense. In particular, you see these Bayesian scores are a lot closer than these, because the larger number of reviews helps to boost these few number of reviews help to bring these numbers down. We also see that this 4.5 star with a lot of rating is the best combination. It got to be number 1. We also see that this one, because the average rating is so high, so even though the average number rating is small, still it retained a relatively high position, number 2. And this number 3. The last thing we want to observe here is that, you see, how come that this product, which has both a slightly larger average rating and a slightly larger number rating, actually becomes worse than this? So if I just compare this product with this product, how could that have happened? Well, the main thing is that because both of their simple naive average rating is below the big R, 4.42. So for those kind of product, if you actually have a fewer number of ratings, then we trust the average more than your own average. And that's why it put up closer than this product to the total average 4.42. So there's a lot of interesting messages just out of this simple example. Now let's move on to a larger example. Now our goal is to reverse engineer what Amazon does. Again, Amazon shows you the average number of stars, a 4.5 star, and number of ratings, and you can try to make sense out of this yourself. Everybody in our mind, we're implicitly comparing this in some scale. We know for certain product 121 is a lot of ratings, and therefore this is trustworthy, and we know for certain product 121 is not enough. So we have some implicit scale that we can use. Now Amazon also gives you a ranking, not just the rating, but also ranking of, say, similar product. Let's say HD TV, LCD TV, 30 to 40, 34 inches. Okay, if you go there, as we did a few weeks ago in 2012, you see that it gives you a ranking of, say, top 20 TV products. And you can actually rank that top 20 by several different criteria. One criteria is the so-called average customer review. And you think that this order, therefore, should be exactly following this average number of stars. But actually, it does not. I will show you an example in a minute. So it must have done something else. What is that something else? That's a secret formula that Amazon does not reveal to the external world. But there must be some formula behind it, and we believe that, one, it must have taken into account the number of reviews. In other words, a Bayesian adjustment has been done. 2, the recency of review also matters. And 3rd, reputation score, or in general, the quality of the review. One aspect of quality review is the reputation score of the reviewer. In fact, Amazon also keeps another ranking, a ranking of people, a ranking of reviewers. Some people actually try very hard to get to the Hall of Fame and be included in the list of top reviewers. In fact, there is a voting formula that has changed about 3 times over the last 15 years. And there's interesting blogs just talking about the voting formula hidden behind the ranking of reviewers. But anyway, reputation score reviewer is one thing. Quality of the review just based on natural language processing, so the keywords another. Review of review is another. And even timing of the reviews with time series machine learning will also help. So all these collectively points towards not just the quantity, but also the quality of the reviews. So quantity, quality, and timing of the reviews, these 3 factors must have factored in. But since we don't know the exact formula, we're going to try to reverse engineer that. Now this is, of course, assuming that there are no other factors such as trying to finish selling something stocked up and not selling well, and thereby just artificially boosting to the top position. There are insider rumors spreading around that says that maybe that has never been practiced in Amazon. So we have some level of confidence that there is a more objective formula. All right, so our goal in the next 5 minutes is to try to discover that. And this is our example. It's actually LCD HD TV 30 to 34 inches. We did not write down the actual manufacturer of the TV because that doesn't concern us here. We just write down the list of 20, okay, from 1 up to 20, top 20, ranked by Amazon according to customer review. But if you look at the customer review, which are these numbers, you see that they are not in descending order. Okay. Clearly, there's something else going on, even though it is according to the customer review, as is claimed. For example, the number of reviews by a Bayesian adjustment. We write in red the number of reviews here. Okay. You can see some product only got 7 or 8 reviews. Some got 249 reviews. Okay. If you look at this table, compared to the last small example of MacBooks, it makes some sense. For example, whatever has a high naive average number of stars and a reasonable number of reviews is ranked high. But there are also quite a few outliers, including those circled in black color. Why is it ranked number 6 if it's only 4.2? Why is this number ranked number 12, 15, and 20, these 3 products, even though the number of their reviews are actually very similar? Okay. This one you may see why, because it's got a small number of reviews and a small ranking score, but 12, 15, and 20, they almost get the same number of reviews, but they're spread very widely in the final ranking order list. Also, why is number 14 ranked so low? It's got a reasonable number of stars and very large review population. Shouldn't it be actually be higher than position 14? So there are quite a few outliers and mysteries. The first one we want to resolve is the Bayesian analysis. So the formula NR plus NIRI over NR. Now, we know the NIs, RIs, and we know the total average Rs. Of course, we also know the total number of reviews, but as we mentioned before in the last segment of the video, this sometimes is N min. Okay. Sometimes this N is N max, which is the largest number of reviews. Sometimes it's N average, which is the average number of reviews received by a product out of these 20 TVs. So we don't know whether we should use N, the total number, or N min, which is what, 8 or 7, or N max, okay, which is 315, or N average, which is 99, and this total is 1986. Which factor shall we use as this N in the formula of Bayesian adjustment? Well, let's try all of them. So we did try all of them and look at the resulting ranking. It turns out that both this and this get very close to the actual ranking by Amazon, this ranking. So we can take these numbers, do Bayesian adjustment in 4 different ways according to what we use in this expression, and we see that this could have been the formula and this could have been the formula. Okay. So that makes sense because these two are too extreme perhaps. Okay, so somewhere between 100 and 300, somewhere between the average number of review per product and the maximum of reviews per product is used in the Bayesian adjustment. Okay. But also, we have to look at the quality of reviews, and that helps explain quite a few mysteries. For example, product 12. The most helpful reviews got 26 people finding it very useful, which is a lot more than product 15 or 20. So that's why 12 is ranked quite high. Or product number 6, ranked number 6 by Amazon. The most helpful review has 139 out of 144 people saying that it's helpful. So the binary count of thumbs up and down is very high, very favorable to the reviews. So people may trust the reviews much higher. And this explains also the position of number 6. So let's take a look at 12 and 6. Okay, here's 6. That's why, even though its score is only 4.2, is positioned quite high. Okay, and we're going to now look at number 14 here. Okay. Why is this ranked kind of low? Well, it turns out if you look at those reviews, first of all, the most helpful review was from 2010. And that's a little outdated. This is for product 14. And there are 8 reviews who gave it 1 star only. So the distribution has a very negative component. And the review text says that the TV actually stopped working, didn't work after a few months. For electronic product, that's a major complaint. So by looking at the quality of the reviews in different ways, we see why 12 and 6 ranked where they are and why 14 is ranked where it is ranked. And then as to the timing, the recency of the reviews, we notice that, for example, product 15, there's a December 2011, which is very close to the day that we pull these data off Amazon. That's very recent. And then as to product 14 we just mentioned, even though it's got a large number of reviews and high scores, the most helpful review was actually still from 2010, which for electronic product may be 1 generation earlier. So this whole set of explanation helped to explain why there were these mysterious outliers. So in summary, the key factors we believe behind Amazon ranking includes, of course, the naive average review score, rating score, but also the following factors. It includes Beijing ranking, probably using the formula Beijing ranking, where n is picked as n average. It includes the penalty on too few or too outdated reviews, depending on the product category. 1 year could be too outdated. It helps a lot to have very high quality reviews. A lot of people review the review as very high quality, or high reputation reviewers reviewing the product helps a lot. And if there are major issues, rating of 1 with a consistent pattern of evidence backing up that rating will push the ranking down a lot. Now, this is not complete science, yet it's only based on 1 example, but it does illustrate some of the factors that goes into the actual rating on Amazon, and partially help to answer our motivating question: when can you trust an average rating on Amazon? And the simplest answer perhaps is that you got to look at the number of ratings too. And this theme of average rating scalarizing a vector and then ranks will continue us to the next lecture on voting. There's still a lot of things that can be done with signal processing and statistical tools for rating reliability on Amazon and other online venues. One key factor that we brought up is this fact of n. It is one of the 2 gains. It's called multiplexer gain in wisdom of crowds. This is just a fuzzy English phrase. So one particular quantification in an unambiguous language is this fact of n, multiplexing gain. From what we saw in Galton's example is that it follows from independent and unbiased individual inputs. They can be wrong, but as long as they're wrong in independent ways, then for a large enough sample size, we will see this fact of n gain. And we'll later see other types of wisdom of crowds.